Alright, 3, 2, 1, here we go. As promised, a pre-recorded lecture about the consequences of the rank nullity theorem. Alright, let's do it. Okay, so let's recall what the rank nullity theorem says. If you have an n by n matrix, then the rank, the dimension of the column space, plus the dimension of the null space is always equal to the number of columns. Alright. So, the main thing, so the first thing we're going to talk about in terms of the consequences is the situation where the rank actually equals the number of columns. Now note, you would want to investigate this because, hey, if that's equal to n, then that's n, then this thing here is equal to 0. Alright, and that thing equaling 0, we know means the null space is trivial, and we've already investigated that the null space being trivial tells me quite a bit about my matrix. So in particular, a matrix being full rank, again, the rank equaling the number of columns, again, coming from the conclusion of the rank nullity theorem, tells me that the columns are linearly independent, and in particular, our system AX equals B will have a unique solution, so long as B is an element of the column space. Alright, so if A is full rank, then the rank nullity theorem does exactly what I just said it was going to do. The n's are going to cancel, we'll get the dimension of the null space is 0, which we know means the null space is trivial, and thus our columns are linearly independent. Now conversely, suppose that our columns are linearly independent. Okay, pick an element out of the column space. By definition, that means that it's equal to an A times X for some X. We want to prove uniqueness, so if we have some other y flying around, then we have this. Subtracting the equations then gives us that. And we recall here that matrix times vector is a linear combo of the columns, where the entries of the vector are the scalars, but these are assumed linearly independent, so it's got to be that all those coefficients are 0, and thus x and y are the same. Alright, so there you go. Full rank gets me the columns are linearly independent, which gets me that AX equals B has unique solutions, so long as B is out of the column space. But it's a taffy, so we have a, oh, look at that. Oh, that's annoying. Oh, boo to that. I didn't put the little slash, and so it got rid of the word proof. Let's get it fixed. There it is. Anyway, so we have a taffy. The following are equivalent. So we're proving now that 0.3 implies 0.1 and closing the loop. So suppose that we know that AX equals B has a unique solution for anything coming out of the column space. Take something out of the null space. Well, that means AX is equal to 0, and we already know that A times 0 is 0. So by our hypothesis here, it's got to be that X is 0. Thus, the null space is trivial, so its dimension is 0, and thus the rank is full. Beautiful. Alright, so there we see full rank giving us some nice things. Now, we already knew the rank equaling n forced the columns to be linearly independent, but now we've reframed it in terms of solutions, AX equals B. An interesting result, and one that we're going to make use of, is what happens if the rank's actually equal to the number of rows. Well, if that happens, then it turns out that AX equals B has a solution no matter what B is. Now, note this doesn't say anything about uniqueness. And note that if the number of rows and number of columns were equal, then we would have that every AX equals B has a unique solution. Ooh, maybe square matrices are important. But anyways, on the flip side, if the rank is the number of rows rather than the number of columns, then we can guarantee AX equals B can always be solved. And this is just immediately by noting that, well, if the rank's equal to M, the column space lives in Rm. So the column space is Rm. So, yeah. Any B that lives in Rm is in the column space, which means that it has to equal an AX for some X. And conversely, if AX equals B can always be solved, that means every B is in the column space, and so the column space has rank M, because it has dimension M. So really, this was just pointing out that the rank equaling M happens precisely when our column space is all of Rm. Alright. Now, with all of this talk about solving systems of linear equations, AX equals B, one more thing I included that I forgot I included the slide. So note that for a square matrix now, we actually get a neat little consequence here that AX equals B always having a solution means that A actually has to be full rank. So the square matrix case actually has this nice little consequence that if you know you can always solve AX equals B, it can actually always be done uniquely. And that's just by pointing out that the rank is the number of rows by the previous proposition, but the number of rows is the number of columns, so we've got full rank. And we have too many parentheses there, so let's fix that. Beautiful. All right, and now, like I was going to say, but I forgot to include with that slide, let's fully characterize the behavior of any system of linear equations. So, Ax equals b, there are three possibilities. And now we're actually going to prove them. All right, so if b's not in the column space, then there's no x that satisfies Ax equals b, so there's no solution. If b is in the column space and a has full rank, then there's a unique x so that Ax is equal to b. There's a unique solution. And the third possibility, well, if you're in the column space and your rank's not full, well, if you're in the column space, then you can find a p so that a times p is equal to b, and you can find a basis for the null space. And if we let h be where h is n minus rank a, note that is a integer that is 1 or bigger. Give me a second, I actually have to just answer this text message. Finish the proof in your mind. All right. Dinner. All right. Sorry. All right. All right. Anyway, so if since h is all right, blah. Let me restart. Let's start over. Okay. All right. So if b lives in the column space and the rank is not full, so the rank is strictly less than n. Well, being in the column space means that we can find a p so that a times p is equal to b. And the rank not being full means that we can find a basis for the null space where h here is n minus the rank. Note that's the dimension of the null space, and since n is less than the rank, that means this is a positive integer. So we can actually find a basis. All right. Now, for any x that is a solution to Ax equals b, note that there are solutions because we're in the column space, then a times x minus p would have to equal 0. But that means x minus p is in the null space, which means it's a linear combo of that basis. And there you go. X is equal to that linear combo plus the particular solution. So our system has infinitely many solutions now. Because, of course, for any x, x minus p will be a linear combo. So whatever solutions you have to be these linear combos, and vice versa. Any linear combo here has to be an x minus p. So, there you go. There you go, the actual rigorous proof that a system of linear equations either has no solutions, has a unique one, or has infinitely many, and the form of the infinitely many is given right here. Beautiful. So there's the actual proof of that thing that we knew to be true. All right, now that we know that to be true, and now we know that the proof here of that fact is hinging on the rank being full, it'd be great if I had some way of actually computing the rank of a matrix. Because as I ranted about, you should always think of the rank as the dimension of the column space, but how the hell do you actually compute that? Alright, well, it turns out that there's a way of getting it using reducer echelon form, and that's going to be our next goal. But before we get there, we have to prove a couple of things. Alright, first off, we're going to prove that if you have two row equivalent matrices, their null spaces are the same, which forces them to have the same rank. So, computing rank is connected to doing row operations. So we'll take care of the case of B is equal to E times A, where E is an elementary matrix, so B is one row op away from A, and then you just repeatedly apply it if you're multiple row ops away. Now, if you live in the null space, then A times X is 0, so E times that would equal 0, so there you go, you're in the null space of E times A. And conversely, if you're in the null space of E times A, recall that elementary row operations can be undone, which we noted boiled down to for every elementary matrix E, there's an elementary matrix L, so that L times E is equal to the identity. So A times X is equal to the identity times A times X, and good thing matrix multiplication is associative, because I can then replace I with LE and move my parentheses around in an advantageous manner. And there we go, then X has to be in the null space of A. So if you have a two row equivalent matrices, they have to have the same null space. And thus, by the rank nullity theorem, the dimension of these null spaces would have to coincide with each other, because the number, the rank plus the dimension of the null space is always the number of columns, and A and B have the same number of columns, so this result is true. So the dimension of the null spaces drop out. Oh, I have copied and pasted these from an older source where I've got the null space written like that. I thought I had cleaned them all up. Very professional operation I got going on tonight. And, it's all good. Anyway. There we go. That's better. All right. Okay, so we've now proven that two row equivalent matrices have to have the same rank. So obviously I want to know that for a matrix in reducible echelon form, the rank is something nice, like, I don't know the number of non-zero rows. Well, in order to prove that, we have to prove some things about the row space, but right now, the rank-and-only theorem has nothing to do with the row space. However, as mentioned in one of the classes, one of the students asked, hey, wait a minute, isn't this the row rank, the dimension of the column space? Well, that's what we're going to prove now, because row rank, which would be the dimension of the row space, turns out to actually equal rank. And it turns out that this is a fun example of we're going to prove an equality by actually showing an inequality is true. All right, so row spaces we know are unaffected by row ops, so if we can connect rank to the dimension of the row space, that's be a useful thing to have. And so what we're going to prove is that the rank never exceeds the dimension of the row space. And then we'll prove that this actually forces equality. So trivial case first, if the matrix is 0, then all of its rows are 0, so the row space is trivial, and there you go. Rank is 0, and the dimension of the row space has to be 0, so there you go. So trivial case taken care of. Now suppose the matrix is non-zero. That means the dimension of the row space has to at least be 1, because one of those rows is non-zero, and so there's at least one linearly independent thing in there, so we can find a basis that actually has stuff in it that isn't the empty set. Alright, for each row, that means that it has to be a linear combo of these basis elements. And now I'm going to create two matrices. Matrix C, which is the coefficients that showed up here, and matrix B, which is just the matrix that has these vectors B smashed together. Alright, and now if we look at the JK entry of A, well, that's the Kth entry of AJ. AJ is this linear combo. The Kth entry of these is going to be the Kth entry of all of these vectors, but these are chosen so that, hey, this is going to be the B1 entry of B. This is the BP entry of B. These coefficients are rigged to be the entries in C, and oh, wouldn't you know it, I have a product of these elements added up, and if you look at it carefully, it looks an awful lot like a dot product, so specifically it's the JK entry of C times B. So A is equal to the matrix C times B. Alright, well, right now, this is a lot of just like, yeah, you can do this. How does this help us? Well, everything is chosen very carefully, because now, if I look at the kth column of A, so note here we did the row of A to get this linear combo. If we look at the kth column of A, that's the kth column of C times B. The kth column of a product is the matrix C times the kth column of our matrix. Matrix multiplication times vector is a linear combo of the columns of the matrix with the entries of the vector. This matrix was chosen so its entries were those B entries, and this means that the kth column of A is a linear combo of the columns of C. So that means the column space is contained in the span of the columns of C, but how many columns of C do we have? We have P, which was precisely the dimension of the row space. And since the column space is contained in here, any basis for the column space can only have at most P elements. And there we go. So, kind of a magic proof, where you just get this inequality because I set up appropriately defined matrices and the matrix multiplication just worked out accordingly. So a real interesting proof, and it is very magic, right? Because sort of like these matrices just come out of nowhere. But not too much, because if you just kind of follow your nose, you can easily see why all these things are there. Just the interesting thing is realizing that these matrices B and C that we constructed actually have to product to A. Right. Alright. But anyway, with this in tow, we can now prove that the rank of a matrix is in fact the dimension of its row space. First, let's note that we already proved that the rank of your matrix is always less than or equal to the dimension of your row space. Furthermore, the row space, remember, is the column space of the transpose. by the previous result, we know that the rank of a matrix is always less than a dimension of its row space. The row space of a matrix is the column space of the transpose, and now we've transposed the transpose, so we're back to normal, and that's the rank of A. So, hey, both inequalities are true. Result follows. Alright, so now we've got rank is equal to the dimension of its row space, so the only thing to prove now is that in the reduced row echelon form, the dimension of the row space is something that's easily detected. And it turns out that if you are in reduced row echelon form, your non-zero rows have to be a basis. So, the dimension is the number of non-zero rows, which means the rank of your matrix is the number of non-zero rows in reduced row echelon form. Okay, so if your matrix is the zero matrix, which does count, then the non-zero rows are empty, and there you go. It's a basis. Alright, so now let's suppose that A is not the zero matrix, and let's say you've got some non-zero rows. Since we're in reduced echelon form, that means all the zero rows are at the bottom, so the span then is just the span of the non-zero rows. So now we just need to check for linear independence, so make your linear combo, set it equal to 0. Now, since we are in reduced echelon form, that means there's some point along the columns of the first row where we're 0, and everything below it is equal to 0. Right, because I've got the staircase pattern going on. Well, if I plug k in then, that means that everything zeroes out except for this term, and this is equal to 0, but this leading entry is non-zero, so it's got to be alpha 1 is 0. And then you just go to row 2 and do the exact same argument, and then go down the line and get all the coefficients are 0. And there you go. Non-zero rows are a basis. They're linearly independent, and they span. Alright, and thus as a consequence of this, we find that the non-zero rows form a basis for the row space of A, where B is the reduced echelon form of A. Got too many periods there for some reason. And the rank of a matrix must then be equal to the number of non-zero rows of its reduced row echelon form. Ashley just sent me a picture. She's driving home right now, and apparently there are little chickens jumping around in the back of this car that she's behind. Oh, good. That she's listening to something there. Oh, man. Alright, this is a good video. Ask me to play this for you in class. Anyway. Alright. Okay, so we know the non-zero rows of reduced row echelon form a basis for the row space, and the row space is unchanged by row operations, so whatever the non-zero rows were for B, they're a basis for the row space of A. And since the rank of a matrix is equal to the dimension of its row space, the non-zero rows of B are a basis for the row space, and there we go. So if you want to compute the rank of a matrix, just get its reduced row echelon form and count the number of non-zero rows. Beautiful. So we actually now have a way of computing rank using row operations. Okay. Alright, and like I said, that's sort of the traditional definition of rank, which again I'm very opposed to because it doesn't really extend outside of the world of matrices. Dimension of column space, as we noted once we talk linear transforms, which will be next week, the dimension of the column space is the same thing as the dimension of the range of a linear transform, and dimension of the range of a linear transform is something that, right, there's a lot more meat there to work with, rather than just sort of this reduced row echelon junk. Alright, and let's conclude today with a very powerful result regarding square matrices, and when we talk determinants, this is going to be the money. This result right here is going to, solve everything for determinants. Which is the following: a full rank matrix is row equivalent to the identity matrix, which means we are a product of elementary matrices. So like we noted, the elementary matrices are kind of like the prime numbers, in the sense that for certain matrices, I can always write them as a product of these. So this is kind of like the fundamental theorem of arithmetic, but for matrices instead. Alright, and these are going to be pretty quick, because we've basically already proven everything, but we're just going to kind of put the pieces together. If we are full rank, let's say we've got our ref for our matrix A. Well, we're full rank, so that means the rank of the matrix is n, and the rank we know is the number of non-zero rows in the reduced row echelon form. That means my reduced row echelon form matrix here has n rows that are non-zero. It's got to be the identity matrix. There's nothing else it could be. So we're row equivalent to the identity. So, and again, look at that. I forgot the very professional operation, and Charlie is sitting right outside the door waiting for me to finish. It's going great. All right, last slide. Let's do it up. All right, so suppose we are row equivalent to the identity matrix. Then I can find elementary matrices so that A is equal to the row operations we got to the identity, but multiplying by the identity matrix just gives me the product of elementary matrices. And finally, if we're a product of some elementary matrices, that means you're row equivalent to the identity matrix, and the columns of the identity matrix are linearly independent. So the rank of that is equal to n, as we've already proven at the top of the video. And hey, there you go. Rank of A is equal to the rank of the identity matrix, which is equal to n, and the proof is over. Alright, that takes care of all the little fun consequences of the rank nullity theorem I wanted to go through. So when we get back on in person on Thursday, we're going to review for the exam on Friday, and then next week we'll start talking linear transforms, my favorite. Alright, that's it. See you next time.